This is a talk about the basic internal theory of operation of Fulcro to help people get started with the big picture view while also getting to see some of the internal detail. The 1,000-foot view is that basically in Fulcro you have a user interface and a database. It's pure rendering, so we render exactly what's in the state of the database at any time. And the database is just an immutable data structure, and new databases are based on old versions of the database. And then a sequence of databases gives you UI progress, time travel, support viewer, etc. And so the basic thing you need to know from the 1,000-foot view is if you have a database and you have the UI code, you have a keyframe of exactly what the UI looked like at that moment in time, or will look like at the new moment in time. So this is kind of a diagrammatic view of that. I've got my database, state is changing over time. I have some renderer like a DOM list element rendering that label, and then my UI is just changing over time. And I can go in either direction on this. So, in fact, we can show you a quick demo of this. Go out of presentation mode here. We can go to a card and show you. I've got some card that starts a number in some place, and I can bump along. And at any given time, I can open up some developers tools, and I can just like move forward and backwards in time and see that number changing. And I can even tell it to reset my database state to that point in history, and now I'm back in that particular point. So what we've got on Fulcro is a graph database, a UI tree, and some things called queries and idents. So the normalized database is just made of normal closure maps and vectors, and anything that has a distinct identity goes in the nodes of the graph. The nodes are joined by edges called idents. We'll see demos of this as we go, and then component queries and ident generators um, go on the components, and the UI queries establish the shape of both the tree of UI data and the shape of the UI, and ident generators just establish auto-normalization for data from any source. So this is a big unifying aspect of Fulcro, and it's one of the big advantages. So let's talk about taking this tree, wherever it's coming from, this tree that is queried, and turning it into a database. So let's say we have a couple of components. We have a person component that has a query asking for, and queries are vectors of things you want, and properties are just listed keywords. So it's got a database ID, it's got a name, and then submaps inside of a query indicate a join. So we're going to go from person address to an address component. And so over here in the address component wants an ID and the street of the address. So if we look at the process of converting a tree of data, right? So we have a person that contains an address into the database. We look at the query of the person, and we pull that data into a table based on this ident generator. So the ident generator is just a little template that says, here's the table I want to put this data in, and here's the property that you look at in the tree to figure out where in the table. So what you end up with in the database is a table, which is just this name in this ident field, an ID for that thing, which it has to derive by you telling it where the IDs are in the data, and then the actual entity itself, so the DB ID and the person name of that particular node. Now notice the person address is a property of person, but it's really a join to another thing. So we have another step, and that's that when we go to evaluate person address joins, we have to go and look at the query of address and the ident for the address to figure out where to put this map. So the map that is the tree of data for the address gets placed in a table address by ID, and we use DBID again to look up the ID. So what we put here instead of this submap is an ident. So this is the link. So this is the ident generator. This is an ident. So this is essentially a get in path, right? Person ID 1 would be a get in path for this ident. Address by ID 2 would be a get in path for where we're going to put this submap. So you can see we can kind of recursively walk the tree and pick up the ident generators as we go. And then once we've created that pointer to the other table, we can take this piece of data, use the ident generator, plug it into that table. So this just recursively lets you walk any tree of data using the component queries. So we could back that up, right? Normalize it, graph edge, continue. So some important notes about this is the location of a component's data in the database is path independent. The path that we took to get to that particular piece of data, address by ID 2, is independent of where I put this address on the UI. Right? There's going to be some tree in the UI, and there's going to be some path that I follow to get to a particular address in the UI, but that particular address's data is going to be stored in the component at some path-independent location. It's normalized. So that means any model code that we write to operate on that data does not depend on its location in the UI. And that's extremely important because you want to be able to refactor your UI. You want to be able to move things around and have the model code not break. And so that largely fixes that. And then the UI tree or any other subgraph from this database is just created by following these joins. So normalization allows for multiple components to share state in an immutable database. So you could have a person form, a person view, person list item. All these things could be representing the same person. This is you're editing the person. This is maybe you're looking at all of their details, and maybe this is they're in a list of people. And they almost define the same ident generator, so that if they come in from some place and you say, oh, I'm normalizing a person list item, well, it needs to go in the database where that person goes. But they don't necessarily have to share the same queries, because a person list item might only want the name. Person view might want all of the details of a person, and a person form might only allow you to edit certain things about the person, like their address. So this allows any number of simultaneous and consistent views of the exact same data, but realize that the components themselves don't own any state. They simply display it. They're simply querying for something and defining where it goes if it comes in from some remote location, or, well, for any reason, timeout, whatever. So the ident generators are about automatic normalization of incoming data. The queries are about pulling data from this database, and so we need to see how DB2Tree works, how we're going to take our database, which is a normalized thing, and turn it into a UI tree. And so you could pretty much invent this algorithm yourself in a few minutes, just thinking through it. If you've got a normalized database where we've created all these edges, as you just saw, and we have some root component, we have to root our query walk from somewhere. So I'm going to start with a root component that says my query starts at a friend who's a person. Of course, it looks at friend and then immediately finds an ident which just knows is a join edge. And it can use this get query to pull the query from person to find out which pieces of data from this table entry we want to pull into the tree. So it can pull in the properties, the scalar properties, dbid, and and name. And of course, since we're following once we've followed that join, we also want to make sure that we follow the person address join. So when we get to this component, we see another join. We see the join query goes to address. We go find the address component. We figure out what properties we want out of that and pull them into this resulting map. So it's just a step-by-step follow the graph edge, continue, continue, continue until you've built up a tree of data. So when we can demonstrate this with real code so you can see it in action, in our dev cards here, we've already set up a card that doesn't really show anything except its database. And so we can come over here and we can go to this part, and we can see that we have the address with its query and ident, just like you saw on the slide, person, query, ident, and we're giving here some initial state. Oh, that's actually something I want to talk about before we get into this. So this is how we convert. And so we've got some phases of operation here we're interested in. We just loaded the thing, we're initializing the application, and we want to have something in our database because otherwise the UI doesn't have anything to display at all. So this is a good time to put the UI in a starting state and establish the known initial state. Once we're active, once we've established that state, then we want to bring data from the server, maybe based on session information or other known data like the URI, And we might then also have user events that happen, server pushes, asynchronous events, web workers, whatever, that desire to update the client and or server databases. And so we've got some sort of bidirectional CRUD operations, etc., that we want to happen. And this pretty much covers everything an application wants to do in kind of an abstract sense, right? Initial state, and then once you're active, you essentially, since this model is one of just change the database, the UI shows what you've got. Change the database, the UI shows what you've got. Sort of like a Disney animation, keyframe to keyframe to keyframe, just with the user in control of what happens from keyframe to keyframe. So an initial database is pretty trivial. We've already got a way of composing queries, and so we could co-locate initial state that matters for the components in the same way that we compose the queries. And so here we're showing two components. We've got a root with a query of friend whose initial state is just a map whose friend key gets the initial state from the person component, and the person component has some initial state that just defines some data for a person. So if we run that tree to DB algorithm on that we just walked through a moment ago, we'll end up with a normalized database. So that's where we can demonstrate this briefly here. So we've got a root, we've got initial state of friend, and here we're actually passing parameters to the get initial state. So we can pass in a piece of data and a name, and then the get initial for person pulls the ID and name out and puts it in a map with the proper shape, and then we're not initializing the address at all. So you can see that the database that shows up in this card is the normalized database as you would expect it from the stuff we just showed. So if I reload this, you'll see it kind of starts out empty and then it suddenly populates, and that's essentially all it's doing. So we can go down here and we can actually play with this a little bit. We can see the individual pieces, so we can ask for the initial state of some person where we plug in some arbitrary data. I can run that and you can see the data is just coming back as a map. And I can ask for the query of a person, which is just name, address, and then the subquery of the address. Right? So you can see when I ask for the query of a specific thing, I don't get a get query back. I get the actual tree query back. I could ask for the initial state of root, which I can see I'm embedding friend and Sam in there. I can look at the query for root, which walks all the way from friend down to the address details. And then if you look at this root query, you can see that it's a vector. The first element is this join, and then the friend element of that is the subquery of person. Now there's an interesting thing about that, and this is just an internal implementation detail, but if I look at the first thing, well, that's the friend map, which is the element. If I look at the friend element of that, that's the query of person. If I look at the metadata of that query, I'll see that it actually contains a reference to the component person. And this is how normalization actually works. It can look up the component to normalize just by knowing the query. So it's like I said, just a little implementation detail. Here's the tree to DB function. And so I can tell it I want to use the query from root, the initial state of root, and this just tells it to build the whole database. And so I'll see I get a database with friend, the link to the table, person by ID, 1, and the table data. And then if I take that database into a variable and then run db to tree on it with the query of root, and you have to pass the database twice for an internal reason, I get back the tree that I'm looking for. And of course, I don't get address information because there is no address information. So once active, well, what can happen now? Well, we could do local UI reads, which would hydrate the UI. We can do explicit loads, right? Contact a server and say, hey, I want to read something. We can have the server, maybe through WebSockets, push data to us, or we could have a web worker that's calculating things and periodically updating the UI, etc. And we can have generalized transactions where we'd like to do some sort of abstract operation with potentially multiple parts, local optimistic updates to the state database, and perhaps 0 or more remote transactions or remote interactions. So let's talk about the local reads. This is just db to tree. When we want to hydrate the UI, all we have to do is get the query of root, get the database, run db to tree on it, and we can do that from any root, or the root, or any arbitrary node that has an ident where we can say, okay, this is the node in the graph where we're starting, and that latter part is used for high performance localized refresh. There's a component way down deep in your tree, the state of it changes, we can actually detect which thing needs to update, run the query starting from there, and just update that subcomponent. So this gives you a much faster kind of automatic optimization around both pulling the data out of the database and rendering just a portion of the UI. We can also do explicit loads, and here our queries already define desired trees of data. So you saw a moment ago when I did the give me the query for a person, I can just get that subquery, right? So for any portion of my UI, I might have quite a bit of things in there, but at any given time, I might just want to load a person, I want to load a blog post, I want to load a list of comments, those kinds of things. That's the kind of interaction that actually happens in an application. So if I have the UI-based query, I already have a query that describes the subtree of information that portion of the UI wants, and that the ident generators on those components that are linked into the query know how to normalize it into the graph. So we can potentially target the roots of the incoming tree to some specific edges in our graph. So for example, if I'm loading a person, I don't necessarily want it to go in the root, it might go somewhere else. But the default target is the root node. So for example, a load, and you can do these via any component of the reconciler, a load of the friend key, which is supposed to give me back a person, is going to load a person and the subtree with the address into the root friend edge. Whereas a load of maybe current settings using a settings component, I could target some screen 1, and then the edge screen settings within that. And all of my database is normalized. So this is the table name, this is the ID of the thing in the table, and this is the entry in the table. So these targets are rarely more than 3 deep. Actually, they're usually exactly 3 deep. Either that or 1 deep, 1 or 3. 1, you're targeting the root. 3, you're targeting some field of a node, which is at some arbitrary location in your graph, right? It doesn't have to be 1 down, it can be anywhere. But you only have to go 3 deep because of this normalization scheme. And then of course we could have push from the outside. That could be a WebSocketed worker, whatever. But we can use the same exact mechanism load uses, this tree to DB. And we have a helper function called merge component for this that can take a UI component, a tree of data, merge and normalize it, and of course anytime the DB changes this way, root render happens and the UI self-heals. So basically this is just load, but you're skipping the remote interaction. You already have the tree of data for some reason. So merge component, in this case we're using a reconciler, which is the internal kind of top level thing that controls the UI. Telling what component, oops, I keep double clicking, the component we want to use the query of, the data, and notice this is a tree of data. I've got some person 2 whose name is Bob, whose address is this stuff. And then I can also tell it where to place this edge. So I can tell it I want to replace the root edge enemy. So this, if you compare this to the load, load component friend person, this was placing the person in the root friend edge. This was placing the settings in the screen 1 screen settings. This is placing a person in the root level enemy edge. So it's just graph edges. And then to many edges are also supported. These are just a vector of idents. So your query still looks the same. It looks just like a join, but the node in the database becomes a vector of idents. So I've got friends as person ID 1, person ID 2, etc. And then targeting of loads and merges can use additional targeting methods like append, prepend, replace. So I could say load my best friend from the server, and this would normally default me to a best friend edge on the root node, but I can add an option here that says, and target that to appending it to the current root, I should say friends field. And then the same thing if we already knew our best friend, we could merge a person, Sally with this address, and append that to friends at the root node. So this pretty much gets you any kind of graph manipulation that you want if the data that you're getting is coming in the shape you need it, and typically it will be because you're using a component local query which defines that subtree of data for merging. So let's take a look at these steps. Again, we're just seeing our database here, and I've already shown you we can look at the query, we can look at the database that would be generated, and we can merge components. So I'm going to merge person2 with name Tom, and I'm going to replace the friend edge at the top. So you see person ID 1 is the current friend edge at the root node, and person ID 1 is currently Sam. And so since I'm loading person 2, I wouldn't expect person 1 to disappear from my database. I would just expect this table to get a new row. But I would expect this edge to, instead of pointing at that row, to now point at the new row. So if I run this, you see that's exactly what happens. It adds the entry to the table, updates the edge, and my database is all set to go. Now, on the server, we can go look at part 2. I can define a query handler for a root query for friend that just returns a map of data, like a tree of data. Now, this could come from an SQL database, it could come from Datomic, it could come from whatever data source you want, and you could do this via recursive descent parsing of the incoming query, which is actually available in this environment. You could do it however you want to do it. So this is part of the data-driven aspect of, GraphQL sorts of applications. Is you get the thing you're looking for and a subquery, which again is in this environment, and then you have to construct a tree of data that matches that query to send back to the client. So you can see that this is Clojure code. I am running the server right here. Well, in a REPL. I just cleared the screen of it so you can't actually see it, but it's running there. And so if I go back to the UI and I run this load, here, let me open the network console so you can actually see it does some network activity. You'll see the API request. I could go into the details of this and see that it sent a transit query that looked, it asked for friend with DBI person name, and then it got a response in transit, which is an encoding for Eden Clojure data structures, which got back a map of friends and then the actual data. And you can see in my database, when I loaded that, now I have person 42, the person address normalized, and address is in its own table with ID 5. So it's an extremely powerful general mechanism. I can do any sort of modification to this graph database with just a few basic primitive things. This is the real power of Fulcro and this model in general, is by doing just a few little co-located things, I suddenly get full database management, automatic database management that keeps my data in order, makes it easy to look up. I've got this nice inspect. I'm running this in a dev card, so it can kind of show it to me dynamically, but I've also got this inspect tool where you can do, history perusal. Of course, there's nothing to peruse in the UI, but you can see the database changing as I move around. I can see what transactions have run, etc. And it really does boil down to, loads and merges, making changes to the database, which, as we'll see in a moment, update the UI. So now we've got all the possible kind of remote interactions and how they'll work. I can do a load. I can do an arbitrary merge, which supports then WebSocket pushes or what have you. I get automatic normalization, so I've got database management. I don't have to worry about where the heck the state's going. It all goes into tables, which are all normalized, straightforward. I can refactor my UI. But I still want to be able to push buttons on the UI and have things happen. And so this leads us to application transactions. So all database updates go through a transaction mechanism in Fulcro. They're processed locally. That causes optimistic client database updates, and they're optionally sent to one or more servers. These transactions are just data. They look like calls, but they're quoted so they can be processed locally or remotely, as the model dictates. So the UI is just UI. The model is separate. It's a completely separate code, code artifact. Um, and the join point is this list of things to do, which looks like this right here, a list of what looks like single argument function calls. You can only have one argument. It has to be a map. And notice this is syntax coding, so this is going to be fully namespaced. So bang it together would have to be in the same namespace as this transact is being called from in order for this to work properly. But typically you'll put these mutations in an alternate namespace. I'm going to show them all in one for convenience and speed in this talk, but that's essentially it. So by making them data, that means that I can send this mutation over the wire as well as process it locally without having to do any additional processing of the idea of the transaction. So that's a very important thing, but realize when you're syntax coding here, things are going to be namespaced, parameters will have to be unquoted. So for example, if I want a symbol from an arbitrary expression, the transaction, I could define my people IDs, 1, 2, 3, map into a vector over something that emits these things that look like calls, where maybe I'm saying use an AI to determine who the best friend of this target person is. Notice I'm unquoting ID there on that line of all these people, 1, 2, and 3. And then I can run a transaction on ops, which is a vector of those calls. So this completely isolates the UI from most asynchrony. This looks synchronous from the UI perspective. You run this, the optimistic updates happen right away. The remotes are handled behind the scenes by the model, and when they finish is when they finish. There's a lot of things defined about how that behaves, and you can look at the developer's guide if you want more information on that. But again, this is meant to be a conceptual overview with some code mixed in. So that's what transactions look like, and then mutations are the handlers for transactions. So a mutation can do local optimistic updates to our database, and it has to work on the normalized database. It can send the abstract mutation as data to any number of servers, and the return values from servers can either be ignored, or you can use the same unified technique, normalize, merge, targeting, all the stuff we've just covered for storing the return value data in the client. Because if you think about it, the return value in kind of normal JavaScript apps, you make a callback and the callback gets the return value. In Fulcro, you don't have a callback. It's meant to look synchronous, and it's meant to isolate the UI into this simplistic model of I run transactions and what happens is what happens, but the model defines that. And so the return values of the server need to go in your database. And the only way they can go in the database is if they're a normalizable thing, which means they have to have a query which defines the idents, ident generators, which defines the shape of the result. So this first one, bang it together, is just we're defining that as an action. The state database comes in to an environment via a state key, and this is an atom. So you can swap against it, do whatever you want to the graph database, and then the UI will change as a result of that. And then you can also define that the remote should, if you return a Boolean here, just do whatever the client thinks it did. In other words, send bang it together with the same parameters across to the remote. And whatever that means to the server is what it means to the server. But we can also use params to indicate maybe which person. So back here we were saying use AI to determine best friend, and we were saying what the target person was. And so we actually need to destructure that from the incoming parameters. And here I'm doing no local action. So I'm saying, all right, this is going to be a remote thing only, and I have to pull some additional things out of the environment. And I can thread that through this function returning, which will then hook onto the call the fact that what's going to be returned from the server is going to be some kind of person. And then I can also define, I wish this pop-up would stop happening, with target and tell it where that incoming person should go. So I'm going to put that incoming person on the best friend edge of the target person in my database. So think about that. That's the table ID is the first element, person by ID, which entry in the table, which edge of that entry should be updated. So let's see a little more code running. think I was done with part 2 as far as the code goes. Yeah, so now we can go to part 3. We've got some actual real UI, and I'm going to reload this to make sure it's clean. I was playing with this before starting the video. Okay, so now I've beefed this up just a little bit and added in some UI. So addresses show the address is a street. Person shows a header with the person's name. List item with their age, which shows question marks if they don't have an age. And when they don't have an age, it adds in a button that says invent an age that runs a transaction to invent an age for person with whoever this person is. And then the address, which is rendering this component if they have an address. And then root has a query for who are all my friends, their people, and initially I have none. So in our card we can define a started callback which issues a load to load our best friend from the server and target it by appending it to the list of friends. So if I go look at the server code, the server can define a query for best friend, return what we returned before. And so when I load this, you'll see initially my friends are empty, and then very quickly after that, it fills in with Sally. Hopefully the frame rate on the video is fast enough to see that. And in fact, I could go to the server and just throw in a thread sleep, restart the server to put that in place, and then you'll see there's a second delay where you can see the database is empty, and then the load happens. You saw the network activity down here, and I've got I think that's all it takes to do your initial load. So you can see you're getting a lot of mileage out of this idea that the queries there, notice everything normalized, the address is in its own table, person's in its own table, friends is a vector of idents, so I have a too many relationship here. And so I've got invent an age, which is really just a local mutation. So invent age only does an action, it swaps against the state, it is so sins, person by ID, whichever person it is, and age, some random number between 1 and 55. And so if I press invent age here, you'll see, if you watch right here for person 42, because that's who this is, Sally, you'll see an age appear in the state. And of course the UI updates to now show that age. Okay. And then I have this other button, I need more friends. And needing more friends, we're going to let the server invent a friend for us. So we've created a button here, and we're going to transact, invent a friend. Now notice the UI has no idea. Oops, I need to unquote. Oh, is that right? It's not right. Oh wait, invent a friend doesn't actually need any parameters on the server. Yeah, so this was just errant on my part. Okay, so invent a friend is a mutation that is completely remote. So again, the UI has no idea whether I'm doing that locally or remotely. I could do it locally, I could do it remotely. But I wanted to show it remote in this particular case to just demonstrate all the pieces. So load is an explicit thing which you could trigger in an on-click handler as well, where you know what kind of your root key is or entity. You can actually query by ident here. You could say I want person by ID 22, and then on the server you could define a handler for entities that could pull that person into your database for you. Or you can do a root-based query, which is just giving it a keyword. So you can do arbitrary loads to get things into arbitrary places in your database and hook up edges with targeting. There's also a more advanced thing here called a post mutation that lets you wiggle around your database however you want after the load completes, which is sometimes necessary. But here I've got invent a friend. Again, UI knows nothing about remotes, but the mutation, which again, these go typically in a separate model file. Invent a friend has a remote that takes the AST. This is the abstract syntax tree of the mutation itself. In other words, it's going to have a node in it that says invent a friend. It's going to be, compiler-like stuff. And these helper functions, you can thread the AST through that to say, I want to attach the fact that this mutation on the server is going to return a person, and I'd like to target that person by appending them to friends. So really, that is all the code. I'm not hiding anything here. Over on the server, I've created this random list of people with various random comedic addresses. And so my mutation on the server for invent a friend just randomly selects one of those people from this list and returns it. So you can see there's just almost no code here. And yet I get all this advanced database update functionality. So if I say I need more friends, it just appends them in. Everything normalizes in terms of the people. My list of friends is growing, and I get what I'm looking for. So that's the basic operation of Fulcro. And this pretty much lets you build any application in very short order with fairly complicated semantics, but with quite simple code. So I hope you'll continue learning about Fulcro, read the developer's guide, watch the additional YouTube videos, and perhaps return and rewatch this one as you get a little more experience.